Okay, today we're looking at the second derivative test in concavity, and I will just read the second derivative test instructions here. So it says find f prime and f double prime, which makes sense. You can't find f double prime until you find f prime. Find your critical points, and then it says compute f double prime of c for each critical point c. If f double prime of c is positive, then there's a relative minimum at c. If f double prime is negative, then f has a relative maximum at c. If it equals 0, then the test fails. So try the first derivative test. So for the first example here, this is going to make more sense when we do an actual full example, but this says describe how you determine the concavity of a function using the graph of the first derivative. Well, you're going to find f prime on either side of c. So the point in question, if the function goes from positive to negative, it's going to be concave down, because you would have a situation like positive to negative would mean concave down. And then if it's negative to positive, it's concave up. So that's how you'd find it using the graph of the first derivative. So I'm just restating this. It says, how would you determine the concavity of a function using the second derivative? And this involves a, b, and c, 3a, b, and c here. So that is how you determine concavity. So second derivatives are usually easier to work with. So this sometimes is easier for concavity. But if you are sketching a function, you'd have to find f double prime anyway. So it's a good time to find concavity that way. Okay, so points of inflection, that is when let's look at, I'll see if I can sketch one here right above. So let's say I sketch something that looks like a sine wave. So a point of inflection is where the concavity changes. So you can clearly see right here in this region, this is concave up, meaning it's opening up, and this is concave down, where it's opening downward. So at some point along that line, it changes from being concave up to concave down, and that's going to be somewhere in here for a sine wave. At some point, the concavity changes. So that's called a point of inflection. And the way you find that is to find f double prime, set it to 0, and then you test points on both sides of the critical points. So it's a lot like the first derivative test, except it's in the second derivative. So same process, but the results that you get from it mean different things. So it says if the sign of f double prime switches from positive to negative, then f is concave down. If the sign of f double prime switches from negative to positive, then f is concave up. So the second derivative test relates to concavity and relative mins and maxes of f's, or of f. Okay, so it says when is the second derivative test inconclusive? If it's inconclusive, what do you do to determine you have a local max or local min at a critical point? So like the original statement on the previous page, it's inconclusive when f double prime of c equals 0. So that's when you're going to use the first derivative test to determine if you have a local max or min. So here's our first example. It says determine the intervals where the function below is concave up or down and find the points of inflection. Okay, so this is all about the second derivative test. So let's take derivatives. F prime of x is 3x squared minus 12x. And then f double prime of x is 6x minus 12. So if we set this to 0, we can see that x equals 2 is a critical point in the second derivative. So just like the first derivative test, we are testing values to the left and right of x equals 2. So let's test 1 or 0. 0 is always good. So f double prime of 0 is negative. If we test a number to the right of 2, let's test 3, that would be positive. So this is about concavity. So if it is negative, then so if the f double prime of 0 is negative, so that tells us that the function is concave down on that interval. So if I were to draw a number line again, I put the 2 here, and then goes from negative to positive. It's concave down where the second derivative is negative. So this would be concave down from negative infinity to 2, and concave up from 2 to infinity. And then it says, points of inflection. So this is where the second derivative changes sign. So the second derivative changed sign around x equals 2. So x equals 2 is a point of inflection. Okay, next example. It says find all critical points and apply the second derivative test to determine where you have local maximums or local minimums, or state that it fails. Justify your conclusions. So let's take derivatives. So f prime of x is going to be x squared minus 4x minus 5. The critical points for f prime would be 5 and negative 1. Okay, and I usually do that just in case I need those later. So let's find f double prime of x. This will be 2x minus 4. Critical point there is x equals 2. So we're finding the critical points for both the first and second derivatives. Okay, so around 2, do the same thing we did in the previous example. Let's test numbers to the left and right. Again, I'll choose a 0, so f double prime of 0 is going to be negative. F double prime of 3 is going to be positive. So x equals 2 is a point of inflection. So that's where the concavity changes from upward or downward to upward. Okay. So let me move that a little bit. All right, so now let's see here. So, local maximums or minimums. Well, all we have to do for that is plug in the critical points from the first derivative into the second derivative. So f double prime of 5 equals, is it a positive or negative number? That's the real question. Well, it is positive. And then f double prime of negative 1 is negative. So in the second derivative, you plug in your critical points from the first derivative to get your local maxes or mins. So this x equals 5 is a relative max, and x equals negative 1 is a relative min. So this is a little confusing because we're taking critical points from a first to plug it into the second. And then the second derivative, we set it up the same way, find its critical points, and those tell us different things. So you do have to keep this straight, and you might want to revisit the first derivative test to make sure you can keep that straight.